Hello everyone, welcome to my channel. In this video, I'm going to talk about how to use the spatially constrained lighting and the spatially constrained Noven method to define functional regions like hospital service areas, cancer service areas, or other type of service areas you are interested. You can read my book, The GIS Automated Delineation of Hospital Service Areas. And this video is mainly about the chapter 6. Okay, so first, we need to open the ArcGIS Pro because this tool is developed based on ArcGIS Pro. And first we search ArcGIS Pro and then we can enter this interface. And first we need to create a new project. Just click the map and then we see there is a name. If you want to change that, you can change like HSA book CW4 because I created some before and that's why I need to use this name. So it doesn't matter, you can choose whatever name you want. And then for the location right now, you can specify the location if you want to see whether you save your project. And for here, we just use the default. And also for create a new folder for this project, you can just check or uncheck, both are fine. So let's click OK. And then we can open an empty map here. And they only provide the topo map and here shade, just the very basic stuff. And then we need to go to view and then catalog pane. So we need to find our data and also tools. We right click folders, click add folder connection. And then, so this is my data, already download the data, Florida, October the 1st, 2022, and then zip, there is a Florida folder. So just click and then click OK. So this data has been linked here. So we see there are several folders here, and there are two databases, the FAL Florida HSA, this is a main database, and this is a network database. And there are some tools, Google Map API, using the Google Maps to estimate the travel time to work. And this is the HSA delineation hub model to define the HSA as well. And then these are some other files. So our mainly use this one, the FL HSA and the geodatabase. And here I want to use the zip code area. Okay, zip code area, just drag, choose this feature layer, and then drag into the map. And then I also need the OD flow. Okay, so I mainly need these two data set. For your project, if you want to do if you want to work on the census tract or census block, make sure your OD flows are based on the census tract or census block. Okay, so here I have the zip code. Let's right click the zip code area and to see the attribute table. And we can see there are several attributes, the zip code. Okay, so zip code. And then this is a unique ID for each zip code, and then we will use this field. Okay. And XY coordinates a population weighted centroid of the zip code area. Usually we use the population centroid, but for the finest geographical levels, it's like the grid or census block, you can use a geographic centroid. Okay, so we use the population centroid because for some areas, population just highly concentrated. And for the rural areas, the population just very sparse or very less population even there. So we need to use population weighted centroid to increase the accuracy. And then this is the population. For each zip code, we even have the population density. But I don't think I will leave this. This is just for create a map. Okay, create a map like population density to show your study area. And then these are some automatic shape length and shape area. So this is a zip code area layer. And then let's see the ODO flows. So ODO flows is based on the zip code, okay? So we can go to the right side. We see this is a patient zip Zoom ID. So this is a unique, so this ID is identical to the Zoom ID in the zip code area, okay? And we even have hospital Zoom ID. So this ID is also identical to the Zoom ID here. You see they have a connection, and then you can link those these two layers, right? And then zip code, this is a zip code for the hospital. And then we even have the patient zip code. Zip code, this is the zip code for the patient. And then we have X coordinate, Y coordinate. This is the population which is centroid of the zip code areas. So this is these are corresponding to the X coordinate and Y coordinate. And then we have hospital X and a hospital Y MC. So this means the mean center. Okay, mean center of the hospital zip code. Why? Because one zip code may contain 1 or 2 or 3 hospitals. So we use their mean center to represent the location of a hospital zip code. That's why you can see this value a little bit different from this if you compare them for the same zip code. Okay, they're different. And then we have all of the flows. This means how many services patient receive from their hospitals. In this table, it means how many service from the patient zip code to the hospital zip code. So you can see all flows. We even have some like zero values. So be careful about these flows. Okay, these flows. And then we have just like a composite Zoom ID. This is the patient ID and the hospital Zoom ID. Okay, so total time means the travel time from the patient zip code to the hospital zip code, and the unit is minutes. Okay, this is estimated based on the raw network connected from the U.S. Census Bureau. And this is some other attributes. I don't think we need it. This is a population, and then number of the hospital beds here, and the potential, some other stuff. These are mainly for the half model. Okay, half model. And this is the estimate flow, which means even if we do not have the actual flows, like all flows, right? We do not know how many services patients receive from their hospitals, but we could use a half model to estimate, okay? So the EST flow and all flows are different. So all flows means the actual flow, okay? And when you create an OD flow like this table, be careful about the duplicated records. So which means, let me drag this film to the left. Okay. And then for example, if you have a patient Zoom ID 1 and hospital Zoom ID 20, and then if you, in your table, you need to make sure this one is this composite, this, if I compose these two films together, 120 should be unique, okay, which means the only one row. So if you have, let's say, one more row, like 120, and then you have the different number of all flows, you need to merge them, okay, merge them to one row, okay. So avoid the duplicated rows for the same, from the same zip code to the same, from the same zip code of patient to the same zip code of hospital, okay. So make sure these rows are unique. Since this is the most important thing here. And also, like what I said, this video is based on the zip code area. If you want to do some other geographic units, make sure your OD flows just aggregate on that geographic unit. Okay, so this is our data. And the next, I want to add the tool here, the HSA Delineation Pro. So right now we can go to see, take a look at this, under this toolbox. It has built a spatial adjacency matrix, calculate the regionalization indices, consolidate flows at the HSA level, dot method to define the HSAs or HRRs, network community detection method like the SC Leiden and the SC Loven. So for the build a spatial adjacency matrix, when you define the service area, if you want to make sure they are spatially continuous, so you need to build a spatial adjacency matrix. So this is based on the Rook continuity. I think it's Rook. Yeah. So this is based on the Rook continuity of your polygon layer, like the zip code area here. And the second one is calculate the regionalization indices. This tool is mostly like you already have a service area, but you have some flows, and then you want to calculate the localization index or average travel time or compiled list or population for the service area. You can use this tool. Okay. So this tool is mainly used just you want to calculate some indices, regionalization indices, and consolidate flows at the HSA level. So this is mainly used like you have flows at the zip code level, but you already have an HSA layer as well. And then right now you want to define the HRRs. So you can aggregate your flows at the zip code level to the HSA level for the HRR delineation. So this is the third tool. The first tool, autonomous method, I will talk about that later. But in this video, I mainly want to talk about network community detection method. This contains two tools. You see the SC Leiden and SC Loven. So right now, I want to add this toolbox to the toolbox. Okay, so just expand this one toolboxes and right click. Okay, right click, add the toolbox, and then go to this folder, Florida, and click HSA Delineation Pro.tbx, and then click OK. And then we can go like first, and let's see the network community detection method. So we just double click. Oops. Just a double click. And then we see where enters your processing pen, right? So after you enter, get this tool, you right click the properties. For example, right now I want to use network community detection method. Go to the tools, make sure the toolbox, the path. Okay, let's go. Let's see here. So you see there is a name and label and also toolbox. So make sure this toolbox, the path, refers to the right path. Okay, make sure your toolbox is really under this path. Okay, this is another thing, and I think that's it. This is just for like execution parameters, some kind of that stuff. So just make sure the path is correct. Okay, path is correct. And then we double click this tool. You can see the interface is very neat. So we need the input polygon layer. So this is usually like zip code area. And then we have the unique ID filmed. Population filmed is optional, which means you can use population, or if you don't want to use it, you just leave it blank. Input edge file is the OD flow. Origin ID, like for here is the patient Zoom ID. Destination ID is hospital ID, and then service flows, just like service flow. And then distance and travel time is optional. And you see the delineation method, I have the default one is the SC Leiden. But if you click this one, you see there is a SC Loven. Okay, so they're actually the two methods here. And then you see there is an input resolution, because for these two methods, they are scale flexible. So you can change the resolution to generate the different number of HSAs, for example, in this study. And then you can see you can impose a spatial contiguity. If you want to make sure your final output will be spatially continuous, choose yes. And then if there is another option, no. So if we choose no, we do not do any other parameter setting. So it's gonna be like just output the polygon layer, which is the HSA. Okay. So if you choose yes, there are more parameters because we need to specify spatial adjacency matrix. So this matrix will be generated by the tool I just introduced. And this is a threshold size, is optional. Sometimes people maybe the default value is 1,000. If you think this value is a little bit small, you can increase like 10,000 or 5,000, whatever, you can do that. And when you use the threshold size, it just means you are, for example, here 1,000, which means your final result, the HSA, the population size for each HSA is more than or at least 1,000 for the population. So if you want to use this parameter, you need to make sure you have a population field here. Okay. So because otherwise, the threshold could not find the field, and there might be some error in this tool. Okay, because the threshold size rely on the population field. And then this is the same. So, all right, after I introduce this tool, I think I can show you how could we run this, okay? So usually after you load this data in ArcGIS Pro, they will give you an option, okay? So this is a layer. If you do not want to load the data in ArcGIS Pro, you can just browse the file and go to your data and choose your data, okay? So for here, unique ID is a Zoom ID. As population field is population. And then input edge file, you need to go to the Florida folder. I think even under FLHC, and then you see the audio flows, click it and click OK. And then you can load the data here. And then original ID is a patient zip Zoom ID. Okay. So this is a destination ID, hospital Zoom ID. And then you have the service flow ID. Here we choose all flows because this is actual utilization of inpatient care. Okay. And then distance, we can choose total time. And for here, we just choose the delineation method like SC item. And the input resolution, you can set any number more than 0. And the default one is 1. And then you can impose the spatial contiguity. So for here, if I choose yes, I need to define a spatial adjacency matrix. And then threshold, let's just define a not spatially continuous one. Okay, let's try how the result will look like. Okay, so we can set like non-spatially constrained HSAs 1. Let's see how the result look like. So you see we got the non-spatially adjacent. So this result will be automatically loaded in ArcGIS Pro. Right click and do symbology. And let's see, we use unique values. We wanna use the HSA ID, and then we add this data set, and we will see something might be different. So depending on your data. So you see, we have a very small one. This is like a donut. Okay, this is like a donut, I should say. And then there is something else here. And then we see in this case, okay, maybe this case is not very classic to ensure the spatial contiguity. If you want to use your own study area, maybe you find the enclaved HSAs, some HSA, for example, here maybe have a small patches linked to somewhere far from this HSA, or like this one, there is a enclave, right? This is a enclave. And then right now, let's try to use the spatial adjacency matrix contiguity. You can change the resolution. Let me change the resolution to 4 and see how the results look like. So we still do symbology for this result, and then let's see if we choose the unique value, how the result look like. So maybe this color is too few. Let's just show all color, and then we can use. I think there is more colors here. So we could see. Let's see. You see, there is a HSA. There's more patches here, right? They are not spatially continuous. So when you change the resolution, you will find more cases. And right now, the donut HSA disappear. And then I think most HSA are spatially continuous. So depending on your data and also study area, okay. And then this one, you see there is a small patches here. They are not spatially continuous. And maybe this yellow one should belongs to the green one. Okay. So this is just for how to use a tool to generate the HSAs that are not spatially continuous if you want to do that. And then when you so after you run this tool, let's see how long does this take. It only takes 7 seconds. It's really fast, right? And these are some messages. If you want to know the modularity and also resolution equals to 4, you can go to the message. Okay, view details under at the bottom of this tool, and then click this one, go to this window, and then you will see, okay, in the study area of Florida, there are 983 zip codes, and then there are 37,000 flows, and this is the flow volumes. And then they even tell you the total population and that's deletion zip code 208, which means 208 zip code, they contain hospitals. Okay. And then you see right now, because we do not implement the spatial contiguity, there's just the original Leiden method generated 38 HSAs with a majority of 0.8. It's actually it's high, right? And then you see these are some messages. Okay, these are the messages. And then after we generate this layer, I want to show you the attribute it has. Okay, so here we right click the attribute table. We see the HSA. This is the first case I use, right? I use that one. So here we see they have HSA ID. So right here I have 19. So I think it ranges from 1 to 19. Count Zoom ID represent how many zip codes in each HSA. Population represent the population in the HSA. And then ARI value. ARI value actually represent the local utilization rate, which means you define a HSA. You want to calculate the ARI. So ARI is a ratio of all of the service volumes within the HSA divided by the total service volumes originating from the same HSA to any other HSAs. Okay, so the ARI just ranges from 0 to 1, and estimate time. This is estimate how long people traveling in the HSA. Okay, so the number Zoom ID represent how many destination zip code they have. Compatibility is a correct ratio of parameter and area. Okay, so this is kind of like small value is better because it represents these are more compact. Okay, more compact. So this is a really important property in the visualization method. So you can see they already calculate all of the index for you. So you don't have to calculate it by yourself. Okay. So this is a case using case do not use a spatial adjacency matrix. So what if now I want to choose yes? So I need to define the spatial adjacency matrix. So I think we can go back to the tool, build a spatial adjacency matrix. And here you see, this is the interface and we have the input polygon layer. Here I use the zip code area. And then the unique ID is just like the Zoom ID. Okay. So when you use the network community detection, you want to make sure this unique ID is the same as that unique ID. Okay. So for the non-adjusted one, we have two options, yes or no. So the default one is no, okay? So the default one is no, which means if, like for example, if these two polygons, they share the borders, right? They will be spatially adjacent. So they have the ID here, 80, and this is 81. That means when you create a spatial adjacency matrix, they'll be linked and they have weight like 1. But for here, you see this one are not physically connected, this zip code and this zip code, right? So when you create a spatial adjacency matrix, the weight will be 0. Okay, so this is a major difference. And here we can try to use yes. Why? Because you see these two zip code, even though they are not adjacent, but they are connected by the physical road here. You can see there is a base map, there is a road. And even for this zip code and this zip code, they actually have a road, okay, 700 along these two zip code. And I think, let's see, for some other cases, even here, okay, so this is actually some water conservation area. But you see this zip code and this zip code, even though they are not physically connected, but you have, okay, this one. So you will see there's a road connected them, 84. And this is a road connected this one, 27. Okay, so these are the cases why we want to adjust the spatial adjacency matrix. Because in the real world, they're actually connected, right? Either based on the, I think this based on the road, but we can also see Tampa area for this one. These two zip code actually are not connected, but they are connected by the like bridge, right? Bridge. And this case and this case as well. Especially this tool, the adjusted or not adjusted, very suitable for the areas that are very fragmented. Like the zip code just are fragmented by the water system or river, lake, or some like farmland, I think farmland here, or forest, okay? And then there is another case we need to consider. For example, here, okay, so here is one zip code. Suppose this is zip code, this is another zip code. Even though they are not physically connected, but maybe people live here take the water transportation from here to here, right? So it's possible to link them together. But if there is multiple zip codes in the mainland, how could I choose whether this one connected this one or the second one? Okay, suppose we have two zip codes, okay? So we just measure the Euclidean distance. If this one, okay, is this zip code is connected to this zip code, we will link them together. Otherwise, we will link this one to the second. So this is a kind of like basic criteria. How do we adjust the spatial adjacency matrix? And right now, suppose we want to adjust the spatial adjacency matrix, you need to input this adjacency file. So we can already prepare one here. the Florida polygon adjacency appended. This is like a CSV file. So we can go there and take a look what's inside. Okay. So this is a CSV file. You can open it up directly in the Excel. So you see, this is origin Zoom ID. This is the destination Zoom ID. Okay. So here, because we only list the zip code should be connected, which means this zip code and this zip code, they are connected. If they are not connected, they will be not listed in this table. Okay. So we can see there are only 34 pairs. We need to adjust it. So when you adjust create this folder, you can use the Google Maps or some like Topo map as a base map to help you identify whether the zip code are connected. And right now, because I already projected this one, so you don't have to do anything if you want to use the data in Florida for practice. Otherwise, you need to create by yourself. And then the output file is where we need to store the spatial adjacency matrix. Let's go TRZ data. Let me delete this data. So we go to this folder, we can create a Florida SAJ up one. Okay. This is just like, okay. So here, be careful. We need to use MPZ, okay? Why do we want to use the MPZ file? Because MPZ is a file format to store the array data, which is very capable to deal with the larger adjacency matrix, especially they want to consume a lot of computational power. So we can use the MPZ file to efficiently compress our data. Okay, so we can run this tool and see how long we can get. Oh, it's very quick. So we can see here only take 2 seconds. And then they even tell you, you have an output file path. This is the MPZ file we will use in the network community detection method. And then they also tell you your corresponding CSV file. I generate the CSV file because I wanna, if you wanna double check whether you do something correct, you can go through this table. You see there is original Zoom ID, destination Zoom ID, and the weight equal 1, which means they are connected. Okay, they are connected. And here, if you want to double check, visualize how they connected these two columns through the weight 1, you can use the XY to 9, which means you could give the coordinates of this column, and then you use the XY to 9 in the ArcGIS, use this one flow, a weight as a flow, and then you can create a flow map, and then you can identify whether they are correct. But here, right now I use adjusted, so I just want to show you whether I did something correct. So here I can just one that is not, let's say, so I just generate one. I don't use the adjusted matrix, and then I just run and go to see what result I get. Okay, so this is one use the spatial adjacency matrix using the adjusted spatial adjacency matrix. So we can go down. And go down. So we can see we actually have 5216 because there is a head rows. And then we can open the one that is not adjusted. So we just go down and see, okay. So here we have 51, 14, 48. So we can calculate the value like 15, 2, 1, 6 minus 15, 1, 48. And then we see we have 68. So how about our original appended matrix? Let's see. We have 34, right? Y is double. because for here, like for this one, so I can, because for the same pair, they will have two rows. So we can go to take a look. So for here, 667, and then we have 108, right? And then this could be opposite. Okay, so we can choose this one, and then we see let's do it again. Let's see 108, right? Because they switch their order, and then they can generate just like A link to B and B link to A. That's why their number is double. Okay. So let's just close. And then we can go back to our network on community detection method, because I already run this one. So let's go to the analysis, go to the history, and then we can click this one because we already set some parameters. We don't want to set it again, and then we go to impose spatial contiguity here, yes. And then we input MPZ file. We go to the T result, and then we use the updated one. Just click OK, and then you see we can have the threshold size leave like 100, doesn't matter, and then here we can use this. Okay, and then we see what we get. Wow, it's quick. So view details only take 9 seconds. And then right now you see there one more sentence that C-Leiden generates 38 HSA with a modularity 0.74. You see the modularity decreased because there are some spatially non-adjacent HSA. So that's why this comes at some cost. Okay, so the resolution is 4. And then let's see the result. I think I can do a symbology and see how the result look like. Then we do a symbology. We go to unique values, and then we set HSA ID here. So if we want to change more, get more color, do this one. Okay. So let's see the result, how the result look like. See, this is our result. This is a spatially adjacent one. And right now you see these two, this patch and this patch, they are connected. Why? Because we create a link here. That's why they can connect it. And also for these areas, because we adjust our spatial adjacency matrix, that's why they're connected. Otherwise, I think they will be separated. Yes, they will be separated. And even for this area, even though they are not connected, because there might be some flows, people stay here, and then people stay here, therefore they seek their in hospital care by them as local areas. Okay. So you see here, you can even open the attribute table, and then we see how they are arranged. 0.59 is almost a half. Like more than 15% of the people stay local for the hospital care, or say inpatient care, and then 0.85. And then we can see the population ranges. So right now you can use 100, or you even use the resolution 1. So how could you decide the threshold? So if you say, I set 1,000 here, okay, 10,000, okay, 10,000 here, but this will not work. Why? Because the minimum population is 40,000, right? So if you say, I cannot set 2,000, I think it will work. So let's just try and see whether it works. Okay. And still very quick. So we can go to the attribute table. We see the population. Right now it's 53,000, right? That means this works. Okay. So this is for SC ladder method. For the SC Novan is the same. You just choose the delineation method and you change the resolution value, like 1. And you can either impose spatial contiguity or not spatial contiguity. And then spatial adjacency matrix, you don't have to change it because this is for the same study area. And for the threshold, we can stick with the original threshold value, default value. And then right now we're do like, I think because we do SC, Novan, SC, okay. So let's just take a look how could this result be. Okay. And then we view details. You see right now the get resolution the 1, and then the majority 0.7 lighting HSA. Okay, so we can go. This is pretty much similar depending on which method you want to use. Okay. But from our understanding, the SC lighting is more computationally efficient, and also seems like it has a higher localization index, and also it can remedy the deficiency in the SC domain. Although this SC lighting method comes out later. So you can see here for this attribute table, they have the same HSA, same attributes, okay? The same attribute filmed, okay? Not their value. Their values are different. So here we can see the population, minimum population 40, maybe 1,000 doesn't work. You can increase the population threshold size, or you can change the resolution. So I don't wanna run more details because all of the things that are pretty much similar. And then from this tool, we can see we can do multiple things. First, we can use these two methods to generate non-spatially contingent HSAs, right? Because we can choose, no, this is one option. Another option is that for both methods, we can change the resolution value, right? And then for both methods, we can generate the spatially continuous HSAs, right? Because we can set the spatial adjacency matrix, and we could even you could even change the threshold size, right? Those are the composition of these two methods, which means we can generate, HSA, they are not spatially continuous by two methods. HSAs that are spatially continuous by two methods, also by the different resolution, by the different population threshold size. So depending on your research purpose, also study area. Okay. So I think we can stop here.